I thought I had automatic. Thank you for catching that. All right. So for those, since I just started recording again, for those who are watching the recording, please do the online survey. If you haven't already, there will be a little bit of extra credit for, there'll be a little bit of extra credit on a practice assignment. And on today's practice assignment, people know how to recognize and manipulate common Taylor series. I want to talk a little bit more about the concept and how to apply it. So it starts from the very definition of a derivative. You've got some function, it's got a slope, and so you could say that that slope is equal to the derivative. In fact, the derivative is defined as the slope at that point. Once we do that, we can approximate the function in that region with its derivative, with a line that has that slope. So if I were to zoom in on this and redraw it, this is a zoomed in view. Then we would draw a line here, and the line should be tangent if I had been using rulers and everything. And for a while, the line matches it pretty well, but eventually diverge from each other. So we see that the tangent line almost matches for a while. Well, then you could say, all right, well, let's make it a little bit a better fit. Let's add a quadratic term. So instead of just saying that f of x is approximately equal to, if I call this x naught plus x minus x naught times the derivative evaluated at that point, let's add a quadratic term. So we're going to add 1/2 the second derivative and if we do that, then we will approximate it more closely for a while, but still you will eventually get a little bit of a discrepancy. And so then you add another term, a cubic term, and then you could add a quartic term, and then you could add a quintic term, fifth order, and a sextic term. And then I forget what the Greek roots are for seventh order, but for eighth order it would be an octic term, and so forth. And we could keep doing that. And so what we say is that f of x is equal to the sum from n equals 0 to infinity of 1 over n factorial, partial to the n, partial x to the n, f of x, evaluated at x equals x naught times x minus x naught to the n. And we have to be a little bit careful with some definitions. 0 factorial equals 1, and partial to the 0, partial x to the 0, f of x is just f of x. So the 0th order derivative is basically saying don't even take a derivative. And you might say, well, how do we fit that in logically? What does it really mean? This is just a definition that makes it work, because it clearly works for the first and second and third and so forth derivatives. Are like, you know, we want to fit it into this series, and we want to fit it in a way that doesn't mess with our definitions, that enables us to write it down neatly. Okay, we'll just say that this is what the 0th order term is. Any questions so far?
Yeah, I have a question for the second derivative. You have x naught squared. That's supposed to be like outside the parentheses, right?
Oh,
X
yes. Thank you for catching
cool.
that. And that was my attempt at erase. I'm still learning the eraser on this. You know, I know how to use chalkboard erasers, but after 6 months of pandemic, I'm still not able to necessarily use tablet erasers correctly. Any other questions? Well, a common mistake I sometimes notice is that if we write this out to just a few terms, because we often just approximate to a few terms, many people will write that f of x equals f of x naught plus partial f partial x times x minus x naught. And what they don't do is they leave out this part here, all right? They leave out the part where you evaluate the derivative and you just come away with a number. You don't come away with, I mean, when you evaluate the derivative, you get a formula, but then you plug in a particular value of x equals x naught, and you just get a number. And I want to show why that's wrong. I'm going to have you work through an exercise on this on Friday, where you will evaluate the first few derivatives of a function that shows up a lot in physics. And you're going to walk through doing it the right way. I want to show you what would happen if you did it the wrong way. All right, let's take e to the x. We know that if f is equal to e to the x, partial f partial x equals e to the x, and partial squared f by partial x squared is e to the x. All the derivatives are e to the x. It's a special function that way. So what I'm about to do is wrong. This next part is wrong. All right. I want to be very clear on this. If I had thought ahead, I would have done a university administrator cosplay, you know, dressed like my least favorite administrator to say, just to emphasize how wrong this is, you know, to show you that someone who doesn't know what they're talking about is doing this. But I didn't think in advance for that. But this next part is wrong. All right. Let's say we were to try to write out the series that way. Well, we would get f of x is e to the x. And so we would have that f of x is e to the x, this is at x naught, plus e to the x times x minus x naught, right? Because that is the derivative. And after all, e to the x is equal to e to the x at x naught, right? Whatever value x is, if x is x naught, this is the logic that some might use. And then we would have 1 over 2 times e to the x times x minus x naught squared. We have 1 over 3 factorial e to the x, x minus x naught cubed, and so forth. And just to emphasize how wrong this is, pretend I'm an administrator saying this right now. Not a professor, but you know, an administrator. You can, I won't name which ones I think might be most wrong. I'm just trying to emphasize how wrong this is, all right? But I've seen people do things like this on tests. They take the entire formula for the derivative and they just use that formula. They don't plug in x naught. All right, they don't say, oh, well, this is e to the x naught here and e to the x naught there and e to the x naught there and e to the x naught there. They just keep going on with this. And so what you would wind up getting is e to the x times 1 plus x minus x naught plus x minus x naught squared over 2 factorial plus x minus x naught cubed over 3 factorial and so forth. And other than the fact that this first term should really be, what you basically got here is e to the x minus x naught. This is exactly the Taylor series for that. So what we would somehow come away with is the conclusion that e to the x equals e to the x times e to the x minus x naught. Or if we canceled, we would conclude that 1 equals e to the x minus x naught, which is clearly not true in most cases. It's true if x minus x naught is 0, but it's certainly not true in general. So don't do that. Here's the correct way to do it. The correct way to do it would be to say that f of x is equal to e to the x naught, that's f of x naught, plus e to the x naught times x minus x naught. This is the derivative. Plus e to the x times x minus x, sorry, x naught, my bad. E to the x naught times x minus x naught squared over 2 factorial, plus e to the x naught, x minus x naught cubed over 3 factorial, etc. That would be the correct way to do it. Because now what you've got is e to the x naught times 1 plus x minus x naught plus x minus naught squared over 2 factorial plus x minus x naught cubed over 3 factorial, etc. So what we're left with is e to the x on the left side, that's f of x, e to the x naught, and then this is the series for e to the x minus x naught. And if we simplify the right-hand side, we get x naught plus x minus x naught. Those two terms tweeted something terrible, so they're canceled. And we're left with e to the x. Any questions? Any questions at all?
With Zoom, I'm not able to see the very bottom because of Zoom's overlay. So I guess right now and in the future, if you have important information at the very bottom, would you mind scrolling up a little bit?
Okay, I can do that, but one way out of that Zoom overlay is...
Press Alt, and then you can get rid of the overlay, Eric.
Yeah.
Thank you.
What's the shortcut?
Alt.
Okay.
Or I don't know what it is for a Mac, Sebastian, so I don't know. You're gonna have to find that out.
Okay, I'll try to be more careful about that, but here it is. Any other questions?
I'm just curious, is there any particular reason why it has to be evaluated at x naught?
Well, you can pick any value of x naught that you want. You could decide to evaluate the function, you know, here or wherever. But the whole idea is that you're expanding around that area. You're approximating it in the vicinity
Right.
of x naught.
Yeah, I didn't see the value of x naught being evaluated at that point. I see it now though.
Yeah, the whole idea is that you're just saying that f of x is equal to whatever its value would be there, plus a bunch of other terms that are 0 if you're not at x naught. F prime of x evaluated at x naught times x minus x naught. I mean, this is 0 at x naught, plus 1 over 2 factorial f double prime evaluated at x naught times x minus x naught squared, and so forth. So all of these other things are 0 if we're exactly at x naught. And if we're a little bit off from x naught, we want to know how rapidly it's changing at x naught. Not somewhere else, but at x naught. And it's very important
Right.
that what you're doing is you're not just plugging in the entire formula for the first derivative, the entire formula for the second derivative, but rather you're taking that formula and getting out a number at x naught. Otherwise, you get absurdities like what I did in red and said was wrong. And for those who are looking back at the notes later, this is an absurdity to make a point. Pretend I was cosplaying as whoever you think is an example of an idiot while I was doing that. It's probably a good thing I didn't cosplay for that, because there would be disagreement on which costume I should wear. And no matter what I chose, I'd offend some of you. Let's take another function. Let's look at another function and find its Taylor series. One function that might seem like useless or pointless for a Taylor series is x to the n, because, well, x to the n is a piece of a Taylor series. But remember that these are, the Taylor series is made out of integer powers. What if n is non-integer? All right, well, you know, let's say we want to get the Taylor series for x to the n, where this may look like a parabola, but x to almost any power greater than 1 looks kind of like a parabola near the origin. But what if it's not a parabola? What if it's x to the 2.3, just to pick something arbitrary? So one thing you might be tempted to do is we could say, can we do a Taylor series about x equals 0? And spoiler alert, the answer for this is no, but the answer for a closely related function will turn out to be yes. And I want to explain why this doesn't work. Okay? So f of x is x to the 2.3. Well, f of 0 is 0, so far so good. Partial f by partial x will be 2.3 x to the 1.3, because whenever you take the derivative of a power, you get the power out here, and then you get the power minus 1 over there. So far so good. And the second derivative will be 2.3 times 1.3 times, oh, and this is equal to 0 at x equals 0. So that was easy. 2.3 times 1.3 times x to the 0.3. Okay, and 0 to the 0.3 is also 0 at x equals 0. So far so good. But now let's take that third derivative. We get 2.3 times 1.3 times 0.3 times x to the minus 0.7, because 0.3 minus 1 is minus 0.7. And what happens now when we plug in x equals 0? What's 0 to the 0?
Oh no, that's undefined.
Yeah, because this is equal to 2.3 times 1.3 times 0.3 over 0 to the 0.7. There shouldn't really be anything there. Okay, so we've got 1 over 0. Well, not 1, but we've got a finite number over 0, which is a problem. So we can't do the Taylor series of that. But something that we can do the Taylor series for is 1 plus x to the n. So let's say that f of x is 1 plus x to the n. All right. Well, now we can take derivatives of that. Partial f partial x will just be n times 1 plus x to the n minus 1. And partial squared f partial x squared will be n times n minus 1 times 1 plus x to the n minus 2. And negative powers are no longer a problem, because even if x equals 0, let's plug in x equals 0. Well, guess what? These derivatives are still x naught equals 0. Partial f by partial x at x naught is just n times 1 plus 0 to the n minus 1. And 1 plus 0 is 1, and 1 to any power is 1. So we just get n. And partial squared f by partial x squared at x naught is n times n minus 1. And the third derivative, partial cubed f partial x cubed evaluated at x naught is n times n minus 1 times n minus 2. And so forth. So what we get is that the Taylor series of 1 plus x whole thing to the n is the sum. Now we need to be careful. The symbol n has a fixed value. It's not something that differs term by term. It's now something that has a fixed value. So I'm going to have to take this series over some other index. I can do m, I could do l. I'll do j, because it looks different enough. M and n, depending on how bad my handwriting is, can wind up looking quite similar. So we wind up getting the sum from, actually I'm going to rewrite it. One plus the sum from j equals 1 to infinity of j times, n times n minus 1 times ... n minus j plus 1 over j factorial. Because remember, each of those derivatives needs the order, the factorial of the order of the derivative in the denominator, x to the j. And now this series is nice. In this series, all of the derivatives are well defined. And even if your power is, something non-integer, like say 1.7, so that by the time you get to the second derivative, we've got 1.7 minus 2, which is minus 0.3, we're okay. Because 1 to a negative power is still just 1. Any questions so far?
So, and I'm trying to wrap my head around it. So, I understand that you rewrote the power of n as a new subscript j, and you said that it's because n is a finite number, but why?
Because what's in a name? It's because that which we call the integer n would by any other letter still be an integer.
I totally get that. It's just why do we?
If you're really
and
used to,
finite, why do we care?
why am I using j? Because I want to sum over different integer powers of x. Look, I could rewrite this. So instead of saying 1 plus x to the n, why don't I say 1 plus x to the alpha? And then rewrite that as 1 plus the sum from n equals 1 to infinity of alpha times alpha minus 1 dot 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 alpha minus n plus 1 over n factorial x to
The alpha.
the n. What is n? 'Tis neither hand nor foot nor any other part belonging to a number. It's just a name.
Mm-hmm.
All right? That's all it is. It is just a name.
Okay, cool.
I mean, I could change any of this. This is one thing you really need to get used to in physics. You know, in calculus, you've got f of x or y of x. So you got df dx or f prime and y, and you've got dy dx or y prime. Those are pretty much always the names. You get used to that. Well, then in physics, we've got a whole bunch of different symbols for a whole bunch of different physical quantities. Because yes, sometimes we want to talk about x. It's usually a direction, space. Sometimes we want to talk about time, and sometimes we want to talk about frequency, and sometimes we want to talk about electric field, and sometimes we want to talk about viscosity. So we have dozens of symbols, and even drawing upon both the Latin and the Greek alphabets, upper and lower cases, we quickly run out of symbols. And so you just need to get used to the fact that we're going to be calling these things by different names. It's not the name that matters, it's the structure, right? Again, that Romeo and Juliet speech is important. That which we call a rose would by any other name still smell as sweet. That which we call n would by any other name still be the index that we sum over. Any other questions? Well, one question we should always ask is, okay, we've constructed this Taylor series. Now we need to ask ourselves whether or not this Taylor series converges. And if it does converge, does it always converge? Or does it just converge for certain values of x? Because that's one of the most important, that's one of the most practical questions you can ask in physics. If a series blows up, that usually means one of a few things. It could mean that you made an approximation that's only valid in certain circumstances. You know, you were doing a calculation of an electric field in the vicinity of a charge, but once you get, or in the vicinity of some complicated distribution of charges, but once you get further away, certain things change. It could mean that your physical approximations are fine, but your mathematical approximations are wrong. Or it could mean that there is some genuinely interesting physics, that in certain circumstances, things really do blow up, all right? That there are certain things that diverge. All of these are possible, and you need to figure out what it is. It's also important because if you actually want to try to get numbers out of things, you're probably going to be writing a computer program. Will your computer program blow up? Will your computer program run into an infinite loop because it's programmed to keep doing something until the result converges and it never converges? That's an important question to ask. All right, so let's look at these. Let's look at these. Let's do the ratio test. Well, let's first start doing the necessary but not sufficient test. All right? Do our coefficients go to 0 as n goes to infinity? So we've got alpha times alpha minus 1 dot 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 to the alpha minus n plus 1 over n factorial. And we are going to be multiplying by, so as we change these, let's say that alpha equals 1/2. We're going to do that for two reasons. One is that 1/2 is an important case. We take a lot of square roots in physics. And also, these prefactors here very quickly turn negative, all right? And that's important, that they very quickly turn negative, because the numerator is going to quickly start growing, all right? That numerator will start to grow. And the fact that it starts to grow is important because the denominator is also growing. All right, so what we're going to have is 1/2 times negative 1/2 times negative 3/2 times negative 5/2 times, and so forth. We're going to get a bunch of negative numbers, and we're going to get 2 to a power, negative 1 to a power, and then a bunch of odd integers. All right, well, so we've got negative 1 to the n over 2 to the n. So far, that looks like something that's going to be diminishing, but then we've got 1 times 3 times 5 times 2n times dot 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 2n plus 1 over 1 times 2 times 3 times 4 times n. All right, and this thing here, this ratio is going to 1, because just as the numerator is growing linearly, the denominator is also growing linearly, but it's growing about twice as fast. The numerator is growing twice as fast. You might say, well, every time I'm multiplying by a number that's roughly twice as large. If it's roughly twice as large, shouldn't it be blowing up? Yes, except that I've got this 2 to the n. So this ratio is going to be approaching 1. If the coefficients are going to 1, does that mean that all of the terms in our series are going to 1 rather than 0? Is that what it means? Because remember, our terms aren't just all of this. Our terms are x to the n times negative 1 to the n over 2 to the n factorial 1 times 3 times 5 times 7 dot 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 2n. Is it 2n plus 1? 2n minus 1. My bad. 2n minus 1. So the numerator, so all of this stuff here is approaching 1. X to the n. As n goes to infinity, what does x to the n approach?
It also
Infinity.
goes to infinity.
It depends. X to the n can either go to plus or minus infinity or 0.
All right.
It all depends on whether the absolute value of x is greater than 1 or less than 1. Or technically 1. Could also approach that. So, really I should be doing the absolute value here. So there's 3 possibilities. What does this tell us about the convergence of our series?
It either diverges or converges.
Right, but when does it converge?
And x is less than or equal to 1.
Not equal, because if it's equal to 1, if the absolute value of x is equal to 1, then we're going to get something that goes to 1, and we know that these coefficients also go to 1. So we're going to have 1 times 1. We're going to be adding up a bunch of 1s. And if you add up a bunch of 1s, the more you add, the closer you get to infinity.
Right.
Yes, I know a math professor would have a heart attack if I said closer to infinity, but you know what I mean. It just keeps growing. So this Taylor series of 1 plus x to the alpha converges if absolute value of x is less than 1. Now this is actually an incredibly useful. Any questions on any of that reasoning before we use it? You can say it out loud, you can drop it in the chat. All right, seeing no questions, let's use this series. Oftentimes, we want to compute a distance. And so we compute that distance using the Pythagorean theorem. So in optics and anything else involving waves, you often wind up getting expressions like e to the I k square root of, say, r squared plus z squared. Or e to the I k square root of r squared plus z squared minus r. Things like that. And the question we want to know is, if I just wanted to simply plug in the values of r and z, get a number, and be done, great. We don't need to do any Taylor series. But what if I want to try to integrate that? E to the I times a constant times a square root. We could look in some handbook of integrals, and who knows, maybe there's some 19th century mathematician who worked on that. In the 19th century, they worked on all sorts of weird functions. But you know what we'd wind up doing if that were the case? We'd end up writing down, hey, this is the function that this 19th century mathematician worked on. What do we then do? Well, we say the integral of that is some other function that a 19th century mathematician worked on. We write that down. Okay, do we have an expression that we can look at and make sense of? No. It's helpful to take functions like this and approximate them with things that we are familiar with. And so we're going to do that with a Taylor series. Let's say that z is small. Well, then we could rewrite the square root of r. The first step we can do regardless of whether z is small. this is a tautology. This is something that is always true. I just factored out an r squared underneath that square root. And then this is also true always. I could take, since I've got the square root of a product, I could take the square root of the part that's a perfect square. This part here is always true. Any questions on that?
No, we're good.
What?
I said, no, we're good.
Well, you're good. You don't speak for everyone.
Sorry.
Okay. Now use small z approximation, right? What we've got here is r times 1 plus z squared over r squared to the 1/2, which is approximately equal to r times 1 plus 1/2 z squared over r squared. So you can work with that. That would be equal to r plus z squared over 2 times big R. And that is a useful thing. That is something that is much easier to integrate. All right, again, you'd still have to look at some work done by a 19th century mathematician, but the tables of those types of integrals are much easier to understand. There's been a lot more work on that. A lot more people have put effort into simplifying those kinds of integrals and producing graphs that make sense of them. You would learn about this if you study the theory of Fresnel diffraction. Now, we're not going to do Fresnel diffraction here. I just want you to understand that we can take this thing and turn it into e to the I k r, e to the I k z squared over 2r. Here we've got a constant. Here we've got a simpler function of z. Any questions? All right, let's do another one. Similar, but again, useful. Let's say that we want to do e to the I k times the square root of r squared plus z plus a squared. Oftentimes in a diffraction problem, r might be the distance along the axis from the screen, the aperture that you're taking the diffraction pattern of, and then z and a might be two distances in this screen. And a, well, the way I've drawn it, let's just say that r is much bigger than a, which is much bigger than z. So z is really tiny, okay? It starts off being the same process. We have the square root of r squared times 1 plus the thing we were squaring. All right, so far, so good. All we've done is replace z with z plus a. Again, we've just replaced z with z plus a. But now, here's where things get a little bit different. Let's actually write out what this z plus a squared is. So we get r plus z squared plus a squared plus 2az over 2r. And now I'm going to pull out, we're going to say that r and a are constants. And so we're left with r plus a squared over 2r plus 2az over 2r plus z squared over 2r. Now, if z is really tiny, all right, what's bigger, z squared or az? A tiny number multiplied by the same tiny number, or a tiny number multiplied by a bigger number? The question answers itself, as someone typed in the chat, az.
Tiny number times a tiny number
Is the
a
tiniest.
tinier
Yeah.
number.
Yeah. So often people will just cross this out because it contributes very little. And what we're then left with is r plus a squared over 2r plus az over big R. This is approximate, but it's often a very good approximation. And so now we have e to the I k r, e to the I k a squared over 2r. This is just a product of constants. E to the I k a over r z. And this is just really e to the I constant times z. And this we can integrate. We're not going to do that integral today. You've been doing that before. But the point I want you to understand is that this is why we make these kinds of approximations, because oftentimes in physics, we have some sort of complicated expression. We're doing some geometry. We wind up getting square roots, and we put those distances into exponents because we're integrating some oscillating function. And we can make some approximations and take this very messy function up here, which you would not think you could possibly integrate. And strictly speaking, you can't integrate it exactly, and turn it into something that is very, very close and can be integrated using normal rules from introductory calculus.
Professor, I have a quick clarification question.
Yeah.
On the line where you X'd out where it says smaller, is the reason that the term next to it not constant? Or why is it not constant as well?
Why is 2az over 2r not constant?
Right.
Because z is a variable. I see a z in here.
Oh, you only stated that R and A are constants above. Okay.
Yeah.
All right.
These
Thank
are
you.
variables. These are the thing that we might want to integrate over. All right. We're going to integrate over z, which is an oscillating function. Sorry, oscillating function of z. So we can't just get rid of z. It's a variable. It's the thing whose effects we need to look at. But we can say this whole exponent, everything that's changing in the exponent is dominated by the 2az term. This stuff here, yeah, it's huge, but it's constant. So we're interested in changes. 2az over 2r, that's changing a lot. Z squared over 2r, barely changing at all. Other questions? Let's do another example. Example 3. This is a simpler version of something that I've put on next Wednesday's problem set. In statistical mechanics, particularly in the theory of phase transitions, you're going to often wind up with things like this. ln of 1 over 1 plus phi plus 1 over 1 minus phi. Right? These are common. And this is a really messy function to visualize. And it's not at all clear whether this function is always increasing, always decreasing, has a minimum, has a maximum, or what. Well, let's see here. We know the Taylor series for 1 over 1 plus x, all right? The Taylor series for 1 over 1 plus something is 1 minus that something plus that something squared minus that something cubed. So this first term becomes 1 minus phi plus phi squared minus phi cubed. And the second one becomes 1 plus phi squared plus phi cubed. And then let's just see. These two terms cancel. These two terms cancel. And meanwhile, the phi squared, that stays because positive, positive. The ones stay positive, positive. So we're left with ln of 2 plus 2 phi squared equals ln of 2 plus ln of 1 plus phi squared. And this is equal to, this is approximately equal to ln of 2, blah. And then we have to remember what our series is for the logarithm of 1 plus x. ln of 1 plus x is equal to x minus x squared over 2 plus x squared plus x cubed over 3 and so forth. So if we just take the first term, we're left with phi squared. And so this messy thing here becomes just a constant plus phi squared. Any questions? Now, of course, this is only valid for small phi. As soon as we go away from small phi, then all bets are off. But oftentimes, we know the behavior of a system when phi equals 0, and we want to see what happens when we just go a little ways away from that. We want to see what happens when we just change the system a little bit. And if all we want to see is what happens when we change the system a little bit from what we know, then methods like this can work. If we want to change the system a lot, of course you have to use other methods. But this is a common way of approaching things. All right. if there are no other questions on that, then before I go to multivariable functions, I want to say a little bit more about series that don't always converge. We've said so far that series converge, sum of from n equals 0 to infinity of u sub n converges if or maybe I should do this. Let's say that, yeah, we'll just say converges if u sub n are all positive and tests are passed. So we have all of these tests for series where all the terms are positive, and we could say, all right, if all the terms are positive, we're adding a bunch of positive numbers that get smaller and smaller and smaller fairly rapidly, then we have tests for whether or not they converge. But one thing we could ask is, okay, what if the absolute values fail these tests? What if the sum of absolute value of un but u sub n does go to 0, right? It goes slowly to 0, but it goes to 0. And u sub n alternates sign. All right, so one term is positive, the next term is negative. The next term is positive, then the term after that is negative. So what we've got is a situation where you've got, if we just started off here, all right, we start off with this first term. Then we add something negative to it. So our sum, more terms, goes negative. Then we add something that's positive but not quite as big, so it doesn't fully recover. Then we add something that's negative but not quite as big, so it doesn't fully recover. And something that's positive but not quite as big. All right, well, that seems like it should still converge. And indeed, it does. If our terms alternate, signs, so positive and negative, and go to 0, then our sum converges. And the classic example of this is the sum from n equals 1 to infinity of -1 to the n plus 1 over n, which is, this is the series, this is the ln of 1 minus -1, or the series for ln of 2. You just take your series for the ln of 1 minus x, and you plug in x equals -1. And this is a series. Now, there are plenty of series where you have alternating positive and negative terms. Sine and cosine are classic examples, alternating positive and negative terms. But those positive and negative terms go to 0 so rapidly that even if we, they go to 0 so rapidly that we don't need the alternation for the series to converge. Even if they were all positive for whatever reason, the series would still converge. Even if they were all negative, they go to zero so rapidly, the series would still converge. I'm going to share my other screen. Let's look at a series for ln of 2. So we're going to do a sum up to n max of -1 to the n plus 1. I've pulled out the negative, the 1 or a minus sign here. -1 to the n plus 1 over n. If we just look at the sum with the first few terms, on the screen here, it doesn't look, well, let's play with our magnification. On the screen here, it's not at all clear what it's converging to, but if we plot the errors, right? If we plot the errors, then we see that it is the errors are going to 0. Or if I just did that, we see that it's converging towards 0.69 something. All right, you have one term, you get, you have 2 terms, you get this. 3 terms, you get that. 4 terms, you get that. 5 terms, you get that. 6 terms, you get that. 7, you get that. And you see how it's bouncing up and down?
Yeah, most definitely.
Yeah, that means that the way we have set up this series, it is converging. It is converging to what turns out to be the natural log of 2. Everything sounds great so far. Here's the problem. The problem is that these kinds of series don't, you could take this series and we could rearrange the terms. Yes, it does look like a damped oscillator. That's basically exactly what it is. It is a damped oscillator. It is oscillating more and more slowly, except it's not an exponentially damped oscillator, but that is the basic idea. I'm going to go back to writing. Go into my drawing tablet. And here is the problem. I could take that series, and I'm not going to work out all the details. I'm just going to show you the basic idea. You can look at exercise 4.17 in the book. And if you look at exercise 4.17, we could take 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, etc. We could arrange it as 1 plus a third minus a half. Well, so far it doesn't look like we've changed anything. Plus a fifth plus a seventh minus a fourth plus a ninth plus an 11th minus a sixth. And if I sum this series, then every term that I have up here does eventually show up down here. It's just that I've arranged things so that I get my positive values sort of front-loaded. They're front-loaded. And in the textbook, this is one of the odd number problems, so there are solutions, but they showed that this can be written as the sum of 8m minus 3 over 2m times 4m minus 1, 4m minus 3. Basically because if you think about the first trio of terms, we've got, when we go from the first trio of terms to the next trio of terms, 1 over 1, all the denominators increase by 4. Instead of 1 over 1, 3, and 2, we've got 1 over 5, 7, and 4. Or sorry, the first two denominators increased by 4. Then the next denominators, instead of 5 and 7, we've got 9 and 11. These are increasing by 2. So we wind up getting the sum of 1 from m equals 1 to infinity of 1 over 4m minus 3. So like if m equals 1, we've got 4 times 1 minus 3, that's 1 over 1, plus 1 over 4m minus 1. If m equals 1, 4 times 1 is 4, minus 1 is 3, minus 1 over 2m. And that 2m will give you the 2, 4, 6, and so forth. And the 4m minus 1 and 4m minus 3 will give you the 1 over 1, 1 over 3, 1 over 5, 1 over 7, 1 over 9, and 1 over 11. And this thing, this part is apparent just from that. This part is not obvious, but you can work it out. You can show the equivalence of these via partial fractions. And because we front load it, because we have more positive terms showing up more frequently, this thing is not ln2, it's 1.5 ln2. And the reason I'm mentioning this is because these types of series, which only converge because of the alternating sign, series that would diverge if the sign weren't alternating, those series are dangerous. Those series only converge based on the pattern you set up. And if you rearrange terms, you can set up a different pattern that front loads more positive terms or more negative terms, and you could get them to converge to anything, and that's dangerous. So in general, today's lesson is that if you encounter one of these series, you should delve into math books. We're not going to deal with a lot of these series. We're fortunate that there are a lot of places where they don't come up. When we have alternating series in physics, it is often, but far from always the case, that the terms are decaying so rapidly that even without those alternating minus signs, they would converge anyway. But if you encounter something like this, basically you need to delve into math books. Any questions? Okay, so we've spent 2 lectures talking about different infinite series, writing them down, manipulating their terms, adding them up, check when they converge, check to see what common functions we could approximate with them. We don't have to limit ourselves to single variable calculus here. We could do this in multivariable calculus, and I'll show you first the formal statement, and then I will show you a very practical statement of how this is often done in multivariable calculus. The formal statement is you get a generalization of Taylor's theorem that looks very similar to what we had before. For a 2-variable function, f of xy would be f of x naught, y naught, the 0th order term, plus the first derivative with respect to x, evaluated at x naught, y naught, times x minus x naught, plus the first derivative with respect to y, again, evaluated at x naught, y naught, times y minus y naught. So far, it doesn't look like anything surprising. then when we get to second order, at first it still doesn't look surprising, because we would get 1 over 2 factorial, second derivative with respect to x, evaluate at x naught, y naught, x minus x naught squared, plus 1 over 2 factorial, second derivative with respect to y, still doesn't look any different. But here's where it gets different. We have another second derivative. The cross partial second derivative. And then when we go to third order, we get 1 over 3 factorial, partial cubed, partial x cubed, all the things you would expect. Should be 1 over 3 factorial. But we get 2 other terms, because there's 2 other ways that we could take 3 derivatives. Just like there are 3 ways that we could take 2 derivatives. We could take 2 derivatives with respect to x, 2 derivatives with respect to y, or a derivative with respect to x and a derivative with respect to y. So those are 3 ways that we could take 2 derivatives. Well, there are 4 ways that we could take 3 derivatives, because we could take 3 with respect to y, 3 with respect to x here, 3 with respect to y, or we could take 2 derivatives with respect to x and 1 with respect to y, or we could take 1 with respect to x and 1 with respect to y, and I'll show you the easier way that we actually do most of this next time, because we're almost out of time. But I just want you to understand that we don't do a lot of these, but when we do these, people will refer to, you're used to, I mean, it's no great surprise that these are called first order terms. Of course they would be called first order. And of course these would be called second order. But this is also second order, because we're assuming that x minus x naught is tiny and y minus y naught is tiny. So we're multiplying 2 tiny things, 2 tiny numbers. And likewise here, these are all third order, because here we've got the cube of a tiny number. Here we've got the cube of another tiny number. So multiplying the tiny number 3 times. So here we're multiplying a tiny number twice and then another tiny number. So that's 3 tiny numbers. That's why this is third order. Even though this is only first and second derivatives, this is called third order because you're multiplying 3 tiny numbers. And again, 1 tiny number and 2 more, so 3 tiny numbers. Next time I'll start class by showing you the more practical way that we do this, but you should know as a matter of terminology when you're reading things and people start saying, hey, we're tossing out this second order term. The first time I ever heard someone refer to this as a second order term, it confused me greatly because I only saw first derivatives. But all they mean is that they're multiplying 2 tiny things. Any final questions? All right, on Wednesday, I will go over a little more with multivariable power series, and then we're going to do some integrals in polar coordinates. I'll have my usual office hours today and tomorrow, and a lot of the stuff that we did today will be further reviewed on Friday in recitation. Have a good day, everyone. You're free to go.
Thank you, Dr. Small.
Thank you.
Thank you, Dr. Small.
Have a good day, Dr. Small.
Thank you, you too. The lucky ones this time. Every time. Could it be you and me are the lucky ones this time? Could it be you and me? Ewan, are you still logged in? All right, I'm logging out.